Hello folks, today we're going to be talking about motion planning, and in particular we'll be spending a lot of time talking about sampling-based planners. This is the subject of Robotic Systems Chapter 10, and you can find it in this link here. So today we're going to be talking about a couple of concepts about motion planning, configuration space, free space, and C obstacles, as well as a certain type of planners called probabilistic roadmap planners, also known as sampling-based planners. In particular, we'll be looking at two techniques called PRM and RRT, and we'll talk about some of the notions of probabilistic completeness. And we'll also talk about some of the aspects of generating higher quality paths using optimizing planners. So the basic motion planning problem is to try to come up with a collision-free path for a rigid robot or articulated robot amongst some static obstacles. The inputs to a motion planner include the geometry of the robot and obstacles, the kinematics of the robot, and also the initial and goal configurations of the robot. And the output is a collision-free continuous curve connecting the initial and goal locations. We're going to be seeing a lot of images like this, and the idea is that we're trying to reduce the complexity of a robot and all of its geometry to reasoning about the movement of a point. This point is a configuration in configuration space. In configuration space, we're going to be depicting this high-dimensional configuration space as just a two-dimensional image here. Some subset of the space will be known as the feasible space or the free space, and then there's going to be a forbidden region, which is the complement of the free space. The forbidden region can include various types of obstacles and constraints, including collision avoidance constraints, losing stability, etc. And the goal of the motion planner is to connect the start and the goal configurations with a collision-free path, i.e. one that does not exit the free space. So the way that we're going to be thinking about points is that we're mapping these robots and all their complexity and their geometry into a point in some high-dimensional configuration space. And as we've seen before, every robot motion is a curve in configuration space. And so hence we can consider these obstacles that we don't want the robot to collide into as configuration space obstacles. These are subsets of configuration space that we don't want this configuration to enter. So as an example, if we had a very simple example like a Roomba robot that was considered to be just a disk, if we assume that it just translates in the X and the Y directions, in the workspace it has some number of obstacles that it can't pass through, and its shape is a disk. We can represent a point on this disk, for example the center point, as the representation of its configuration. Now if we think about the configuration space version of this, the robot is moving about in just a two-dimensional space. And there's some set of these points in which if the robot were to go to one of those points, it would be intersecting one of these obstacles. So this obstacle B here is just a quadrilateral with this sort of arrow shape. And in the configuration space, if you were to imagine moving the disk here around the boundary of the obstacle and traced out the set of points that the center of the disk would move into, you get the boundary of this sort of fattened version of that quadrilateral. And if you wanted to, for example, go from this starting location to this, this terminal location here, from the blue to the green disks, you'd be trying to go from this blue point to the green point in configuration space. And so a path in configuration space that doesn't intersect one of these configuration space obstacles, or C obstacles, is a collision-free path in the workspace as well. So it would correspond to this path, and a motion that would solve for this planning problem would look something like this. Now, how would we generate something like the previous approach? Well, so grid methods are a very easy way of defining motion planning problems for lower dimensional problems. So for example, if we had a point robot and we wanted to avoid these polygonal obstacles, we could construct a grid, and we could connect either along each of the grid axes, or we could also connect diagonals. So this is known as either a 4-connected or 8-connected grid. We can exclude the edges from this graph that overlap obstacles, and then we can search the remaining graph to create a shortest path, such as the one shown here. If we wanted to then extend this to a disk robot, we can construct the C obstacles. We could then eliminate all of the edges that overlap one of the C obstacles, and then we could search the remaining graph to create the shortest path. As you can see in this case, we're actually going to be unable to reach the target because the target is actually in the C obstacle region of the boundary of this space. Another way that you can try to solve this problem is by still treating the robot as a point, but rather than constructing the C obstacle, we can rather exclude any edges that pass within the radius of the obstacle distance to one of the polygonal obstacles. So even though we're thinking about movement in the configuration space, we're doing the reasoning about geometries in the workspace. And we're going to be doing a similar sort of thing for more complex robots. And it's a good thing too, because actually the complexity of configuration space obstacles can be enormously complex. So if we just were to assume that we have this robot here, it has a shelf in front of it, and let's assume that it can only move 2 degrees of freedom, basically the shoulder joint and an elbow joint. If you were to plot where all of these obstacles lie, if you were to think about the upper arm colliding with obstacles, the lower arm connecting with obstacles, and also the gripper colliding with obstacles, you'd find that the set of spaces that are actually free is this very strange looking set. And in order to find a path from the start to the goal, you'd have to do this rather tortuous movement, pulling this arm out of collision and then moving it towards a point that was closer to collision. And so it's a really complex sort of reasoning problem to construct these obstacles directly. So even if we're looking at higher dimensions, it's even more complex. And so we oftentimes don't want to try to work with C-space obstacles directly. But collision checking is fast. Now, we could try to apply, for example, a grid to this two-dimensional problem, and that would actually work reasonably well. But if we're trying to work in higher dimensions, so for example, with most industrial robot arms have 6 degrees of freedom, the size of the grid is going to be exponential in that dimension, which is also known as the curse of dimensionality. So it'll take millions or billions of points to be able to construct such grids. So the idea of a probabilistic roadmap is that rather than constructing explicit grids, we're going to approximate the connectivity of the free space by sampling points at random and creating this sort of randomized network of paths in the configuration space. So the idea is this. We have some sort of n-dimensional space. We have some set that's collision-free, some set that's not. We don't know what these are. What we're going to do is we're going to start to sample in the space by picking coordinates at random. We do this a ton of times, thousands, tens of thousands of times. Then we can check for collision at each of these points, and each of these collision queries is quite fast. We throw out the ones that are in collision, and we retain these points as milestones. For each of the milestones, we'll check its neighbors, and we'll check the straight line paths in configuration space between each of the neighbors in this set of milestones. And we'll throw out the ones that are in collision, and we'll retain the ones that are collision-free as what are known as local paths to form the PRM. Now we have this graph, and we can now construct, also with a similar technique, local paths to start and goal configurations, again doing collision checking. And now we can search this graph from the start to the goal to find a path from the start to the goal. If one doesn't exist, well, we declare failure, but if one exists, we know that it is actually a collision-free feasible path. So the algorithm looks something like this. We initialize the roadmap with the start and goal nodes. We then repeatedly sample configurations from the C-space with some probability distribution. We then check to see whether it is in collision. If that configuration is in collision, not in collision, then we add it as a new node. And then for some of its neighbors, we try to connect that node to the rest of the roadmap. Now, this can continue until the start and the goal are in the same connected component of the roadmap, or you run out of iterations. You've reached the maximum of n iterations. Note here that this is actually going to be a bit more efficient than the previous PRM that I just showed on the last few slides, because it's going to stop the first time that you find a feasible path. So if you're lucky, you'll find a feasible path early on in this iteration, and so you'll terminate quickly. Now, at the end, if the start and the goal are in the same connected component, then you return the path between them. Otherwise, you say no path. There's several different complexities to the basic PRM procedure. So the first one is, how do we actually sample efficiently to hopefully construct paths from the start to the goal with hopefully few iterations. And we also have to worry about whether or not we occasionally don't find a path between the start and the goal. So this answer here might be actually incorrect. So let's check, when does this work? PRMs don't explicitly compute the shape of the free space F. And it gains a lot in order to... So let's check more deeply, when does this work? PRMs are not explicitly computing the shape of F, but they incur the price of dealing with the uncertainty and randomness of those random samples. And so this is a beneficial choice if a small number of samples is sufficient to capture the shape of the free space. Now, when does this actually occur? Let's dive in more deeply. So some of you may have studied Monte Carlo integration in the past. This is a very effective way for computing high-dimensional integrals. These high-dimensional integrals are hard to solve exactly, and they're also hard to solve using grids because of the curse of dimensionality. So instead, what you can do is define some domain, sample points within the domain, and if these points are underneath the curve, then you can approximate the area under the curve by a ratio of the number of points that lie underneath the curve divided by the total number of sample points times the overall area of integration. The nice thing about this is that the error in this approximation is approximately 1 over square root of n, or it's the order of 1 over square root of n, where n is the total number of sample points. So this approximation factor works regardless of the dimensionality of the integration problem. But there's a little bit of a difference between Monte Carlo integration and PRM planners, in that PRM planners actually have to construct a path, and even though in integration, if there's a small region that you may have missed, it doesn't count much to the integral. For a PRM planner, we actually may have to go through these small regions. And so if we don't sample them correctly, we may lead the planner to incorrect failure. So we're going to introduce a notion called visibility. So visibility is defined by having 2 points seeing each other if there's a collision-free path, a straight line path between them. And so we can also define the visibility set of a single configuration as the set of configurations that a certain feasible configuration can see with a straight line path. So this would be denoted by this yellow region shown here for this highlighted point. There's going to be some notion that we can define about the free space called Epsilon Goodness. So if we were to have a volume measure on our space, then we're going to call that mu. Then a space is known as epsilon good if all of its points can see an epsilon fraction of the free space. More precisely, if we take the volume of the visible set of a point, then that point is epsilon good if that volume of the visible set is at least an epsilon fraction of the whole free space. And furthermore, a space is epsilon good if all of its points are epsilon good. So the nice thing about an epsilon good space, where epsilon is relatively large, is that if I sampled some number of points, the likelihood that those points see the entire space, or a large fraction of it, is going to be high. So, however, this isn't the whole problem. There's also this connectivity issue. So in this space here, this is going to be an epsilon good space with epsilon at least 0.5. Each point can see approximately half of the space. But because the connectivity of the left half and the right half depends on this very thin area here, the connectivity is actually quite poor in this space. So this point over here can only see a small fraction of the division F2. So this point here sees a larger fraction of F2. And this is actually a better point to include in my roadmap if I was trying to connect from F1 to F2. So what we're going to define is a notion called a lookout set. So if we were to take a division of our free space into some two different partitions, the lookout set of one partition is going to be the set that can see a fairly large part of the other partition. So more formally, if we say beta as a parameter from 0 to 1, the beta lookout of a subset of the space is the set of all configurations in that subset that can see a beta fraction of the complement of that subset. And the final definition that we're going to be talking about in terms of characterizing the visibility properties of the space is called epsilon alpha beta expansiveness. The idea here is that not only is the space epsilon good, but also all of its subsets has a beta lookout whose size is at least alpha times the volume of that subset. So this means that for any two divisions, any two parts of a division of the space, a significant fraction of one part sees a significant fraction of the other part. If these values of alpha and beta are relatively large, then it's relatively high probability to sample a point in one subset that can see a point in the other subset. Okay. One interesting thing about these expansiveness constants is that they only depend on volumetric ratios and not actually the dimensionality of the space. So for example, in 2D, we can make expansiveness very poor by putting narrow passages into the space, or we can make the narrow passage crooked, and these will cause lower expansiveness than a very high dimensional space that has very few obstacles. Just another set of examples. For this upper left example, the wide passage in the bottom makes this a pretty expansive space. If you have many narrow passages, this gives you a higher chance of connecting the left and the right halves in the upper right example than just having a single narrow passage. Now, if your narrow passage is crooked, you have typically worse visibility properties than if that narrow passage was straight. And finally, if you have a convex set in any dimension, it's maximally expansive with epsilon, alpha, beta all equal to 1. So essentially, you only need a single point to capture the connectivity of a convex set. There have been theoretical results that have shown that PRMs converge in probability as you add more samples to your probabilistic roadmap. So given some values of epsilon, alpha, and beta that are greater than 0, then the probability that a PRM fails to find a path between the start and the goal is going to be bounded by above by an exponentially decreasing function. So this function will look something like this, and it actually works pretty closely with the empirical convergence rates of PRM. So given some number of iterations, there's going to be some number that you need to get any chance of succeeding. But then once you hit that number, then the likelihood that you succeed is actually going to increase quite sharply. The likelihood that you that you fail is going to decrease. Now, can we ever determine these constants? Well, it's actually fairly difficult to determine them a priori. It's also difficult to determine them through experimentation, and essentially it's just as difficult to solve the probabilistic roadmap planning problem as it is to determine these constants. So although these are constants that exist for these sets in mathematics land, they typically are not actually computed for most planning problems. So in any case, this is more of a theoretical argument than a practical one. For PRM planning to be successful in practice, we need to be able to check sampled configurations for collision very quickly. We also need to check their connections very quickly, and so this requires us to have very fast collision detectors. Actually, one thing that is a bit different from what we've described before in terms of collision checking is that we don't just have to check for single poses collision status, but we also have to check the edges between them. These are also known as dynamic collision checks. The typical approach to dynamic collision checking in PRM planning is to discretize the path to some fine resolution, and then we use a static collision check for each of these intermediate configurations. So for these two endpoints here, we'll define a set of intermediate configurations along the path that have a distance less than or equal to epsilon between them, and then we'll start to do collision checking. The most efficient way of doing collision checking is to check the center point first, and if that is also collision free, then we can bisect and check these other points here, and then finally check at the lowest level of the resolution here. The reason why this is the most effective is because we would actually gain speed if we were to try to prove that a straight line path is in collision quickly. And the most likely way to find a colliding configuration, if we know that the endpoints are collision-free, is to check the midpoint. And by recursion, you can see that it's best to then do bisection and continue to check these midpoints. There is, however, a trade-off when choosing this value epsilon. This is not the same as an epsilon alpha beta expansiveness. This is just a resolution parameter. If this resolution is too large, then we might miss some collisions. And if this resolution is too small, then it'll take a long time to do local path checking. In any case, we pick epsilon so that we are in the Goldilocks zone of being just right. Now, we also need to make sure that a small number of milestones are able to capture the connectivity of the free space. And this gives rise to many different types of non-uniform sampling strategies. There are hundreds of sampling strategies that exist out in the literature right now. And if you want to really make your PRM planning faster, you'll oftentimes spend a lot of time trying to choose one of these sampling strategies in order to make this faster. Another popular variant that we'll be looking at is known as rapidly exploring random trees, or RRT. The idea is this. So we have a start and a goal, and we'll construct a tree rooted at the start, and we'll grow it as follows. We pick a random configuration, qrand, and then we pick the closest node in the tree to this point. In this case, there's only one node, which is the start, and so we pick that as q near. And then we extend a distance delta along the straight line path from q near to q rand. So we'll get to this point at q prime. If this is a feasible path, then we keep it, otherwise we throw it away and continue. So we just repeat this process over and over again. So here we sample q rand again, we pick some point q near, which was the start again, and then we extend from the start towards q rand. Here we've picked another q rand, and q near was that first node that we added, and so we just continue to expand. Note that if we do find a collision between the extension and obstacles, then we'll just throw it out, but otherwise we continue. So this process continues until the tree reaches a neighborhood of the goal, and at this point we try to connect directly to the goal. So this sampling strategy that we're talking about here is also known as a Voronoi bias. The Voronoi diagram of a set of points is a partition of your space into all points which are closest to one of the points in your point set, in this case the set of milestones in the tree. So the probability of sampling a milestone in the tree for extension is proportional to the volume of its Voronoi cell. So if our tree is relatively small, we're going to be expanding near the frontier of this tree first, until we've sampled essentially to cover more or less the whole space, at which point the tree is then going to start to refine and sample more intricately near the middle of the tree. Now, note that this is an artifact of the nearest neighbors approach being used in RRT. We're not actually constructing the Voronoi diagram, although this is an interesting topic for computational geometry. We're not actually building it ourselves. So for trying to encourage our tree also to grow towards the goal, we also may use a goal-biased sampling strategy where you have, for some probability, you sample the goal or a point near the goal as the target q rand. It's also very helpful to oftentimes use bidirectional planning, where you grow one tree from the start, another from the goal, and then if 2 points between those trees becomes sufficiently close, then we try to connect them together. Another really important thing is to use fast nearest neighbor data structures. So rather than having a brute force nearest neighbor data structure so that the algorithm runs in order n squared time, we'll reduce this to approximately order n log n time. So far, we've only been talking about trying to find a path, but as you may have noted, some of these paths can be quite jerky. So optimizing planners instead try to come up with higher quality paths. So we call the first type of planner, which only cares about finding a feasible path, a feasible planner. And for the other type of planners that tries to actually optimize the path, we call them optimizing planners. So we oftentimes have to define some sort of objective function. Oftentimes this is just path length, but the objective function can in general be something more complex. But one question we'll try to answer is if the shortest path in a PRM approaches the true shortest path in the underlying continuous space as we add more milestones. And there's been some theoretical analysis of this question. And in a PRM, if you connect all neighbors within some fixed radius to each other during your connection step, then the answer is actually yes. The shortest path in the PRM does, in fact, approach the true shortest path as we add more milestones. The problem is there's order n milestones asymptotically as you add more points within that radius. So the overall running time of PRM is going to be order n squared. Now, if we do something that has a better running time, such as using k-nearest neighbors to connect to our neighbors in the PRM, we'll have a better running time, but we won't have this convergence property, which is also known as asymptotic optimality. Now, they showed that we can also define a certain dynamic radius that actually shrinks over time so that we retain asymptotic optimality, but we have a better running time, order n log n. Also, we can dynamically change the k in the k nearest neighbors approach by increasing k as we add more points. In fact, if we make this proportional to the log of the number of current milestones, then we can retain asymptotic optimality. For RRT, the answer is, well, no, for normal RRT, because the tree is actually history dependent, and it also doesn't get any better as we go on. So on the other hand, if we were to do what's known as a rewiring step, if we use this RRT star algorithm, then we can actually retain asymptotic optimality. So the general idea is that rather than connecting only the nearest point towards the new random sample, we can create that extension and then try to look for nodes around that newly extended point to try to rewire the tree to find the shortest path to that point. With this rewiring step, we can then retain asymptotic optimality. But this isn't necessarily the most efficient method, and we typically need an excessive number of samples in order to refine an existing path. And it turns out that actually, if you're trying to get within an epsilon suboptimality of the optimal path, you need order 1 over epsilon to the power d samples, which is just as bad as grid search. So one effective heuristic, which has been known for a very long time, is called the shortcutting heuristic. Basically, after you call a PRM or RRT planner, then you can just repeatedly pick 2 points on the path, check that for collision. If it's collision-free, then replace it. If not, we just sample another couple of paths. You do this for a few hundred iterations, and it tends to reduce the most egregious jerks in that trajectory. So if you're to look at the comparison of running times between, for example, RRT star or PRM star with this shortcutting technique, it turns out that shortcutting actually does fairly competitively, if not better, in higher dimensional spaces. So just by running RRT and running shortcutting, and then running RRT again, and then shortcutting, we tend to have better convergence rates than either RRT star or PRM star. Just as a recap, we talked about motion planning and configuration space while doing collision checking in the workspace. We talked about the notions of free space, forbidden space, and C obstacles. We talked about the PRM and RRT sampling-based planners and discussed their visibility properties and how the performance depends on that. We also talked about a few optimizing planner techniques, and most of the techniques that we've talked about today are available in several software packages, including the Open Motion Planning Library, OMPL, also Move It, which is distributed with ROS, as well as Cloud. That's it for today. I'll see you next time.